Recently, we've been looking at trigonometric substitutions. We've looked at expressions involving radical a squared minus u squared, where a is a positive constant and u is some comparatively simple function of x. The suggested substitution is u equal a sine theta, where theta is between negative pi over 2 and pi over 2. In this case, the radical symbol works out to be a times cosine theta. The second involves square root of a squared plus u squared. The substitution is u equal a tangent of theta, where now theta is strictly between negative pi over 2 and pi over 2. The radical works out to be a times secant theta. The remaining variation on this theme will be integrals that involve the square root of u squared minus a squared. In view of our trig identities, it seems natural to try u equal a times secant of theta, but we need to specify the range of theta values, and it's not going to be as simple as it was for the first two. To see what the problem is, it's important to understand why we use the range that we do on the previous two substitutions. Thinking of y equals sine x, if I interchange x and y in an effort to obtain an inverse function, I get something that fails the vertical line test. So what we'll do is this: since the sine is an odd function, if I start at x equals 0 and go both left and right, on the one hand I'll get negative function values, on the other I'll get positive ones, and I'll just go as far from the middle as I can until I would start seeing repeated function values. Starting at 0 and going to the right, the sine function hits its first maximum at pi over 2. Starting at the origin and traveling to the left, I get to the first minimum at negative pi over 2. If I include any more x values, I will begin seeing function values that I've already encountered. That means when I flip it over, the picture would fail the vertical line test. So we restrict our attention to x's that lie between negative pi over 2 and positive pi over 2 inclusive. When we flip this over by interchanging x and y, I now have the graph of a function. This is the arcsine function. In a similar way, if we're going to do a substitution involving the tangent function, looking at the graph of tangent, if you interchange x and y, you get, once again, something that isn't the graph of a function. The tangent is also an odd function, so we should be able to fix this in the same way we fixed the sine, except the tangent isn't actually defined at pi over 2 or negative pi over 2. That means instead of less than or equal to, we'll just have less than here. Just as with the sine, all possible values that the tangent can take on in this picture are taken on exactly one time, so that when I interchange the x and y to get this picture, I obtain a function named the arctan function. So both the sine and the tangent can be handled in a similar way. Thinking of the secant now, the secant is a function that is much less familiar to us than the others are. The secant is the reciprocal of the cosine, not the inverse cosine, just the reciprocal. So we'll think about the range of values that you would use if you were trying to build up the inverse cosine function. We'll use that same range for the secant, and this is where a problem is going to come in. The idea that we used previously, start at the middle and go sideways until you begin seeing repeated function values, is not going to work this time. The cosine is an even function, not an odd function. So if I start at 0 and go a little bit to either side, I'll get something that roughly looks like a downward opening parabola, although it isn't one. When I flip that over by interchanging x and y, no matter how small a piece I'm looking at, it's going to violate the vertical line test. I can't use an interval centered at 0 this time. On the other hand, I do want to make sure that all values that the cosine can manufacture are represented, so I do want to include a piece of the graph of cosine that includes all values from -1 to +1 exactly one time. Since I know using a interval centered at 0 is not going to work, I'll start at 0 and go only to the right. I'll go to the right far enough until I've seen all values of cosine, which range from 1 to -1. So starting at 0, make the input into the cosine larger. When the input's pi over 2, cosine is 0. This is going to be the source of our problem. And then cosine becomes negative. At pi radians, cosine is -1. If I wanted to construct the inverse cosine function, this is the piece of it that I would use. I would interchange x and y coordinates and get the usual picture of the inverse cosine. I'm not primarily interested in doing that right now. I'm really interested in the secant, which is the reciprocal of cosine. The secant is the reciprocal of the cosine, so I've drawn in the graph of the cosine from 0 to pi as a black dotted line. Also, since cosine at pi over 2 is 0, the secant at pi over 2 is not going to be defined. To remind myself of that, I drew a vertical dotted line in at pi over 2. At the beginning of the interval, when x is 0 here, cosine of 0 is 1, secant of 0 is the reciprocal of that. 1 over 1 is 1. So not only is cosine 0 equal to 1, secant of 0 is as well. I'm going to draw in points on the graph of the secant in red. This is the graph that I'm really interested in. As you allow the x to increase from being 0 to being positive, the cosine remains positive, the y-coordinate remains positive for a while, but is decreasing. On the graph of the cosine, it's at pi over 2 that the y-coordinate becomes 0. So between 0 and pi over 2, the cosine is positive but decreasing and approaching 0. The reciprocal of such numbers are positive, increasing, and becoming indefinitely big. The part of the graph of the secant that lies between 0 and pi over 2 is this picture. With a vertical asymptote at pi over 2. On the other hand, cosine of pi is -1. Secant of pi is 1 over cosine pi, which is also -1. So this point is also on the graph of the secant. If I start at pi and move towards pi over 2, at least for a while, the y-coordinate on the graph of the cosine is negative. The reciprocal, the secant, will be negative as well. But as I get close to pi over 2, the negative values for the cosine approach 0, so the reciprocals become negative and indefinitely big. If you are between pi over 2 and pi, the graph of the secant looks like this. This is going to represent behavior that we haven't seen before. Previously, certain quantities were always positive, but that's not always going to be the case now. On the next page, I'll draw my secant picture separately, clean it up a little bit, and then think about some consequences. So to summarize, if the input into the secant is between 0 and pi over 2, the secant will be positive. In fact, it will be at least 1 and probably bigger. If the input into the secant is between pi over 2 and pi, then secant will be negative and will be at least as negative as -1 and probably more negative than that. The thetas that we're using can be written as the interval from 0 to pi over 2, including the 0 but not the pi over 2, union together with the interval from pi over 2 to pi, not including the pi over 2, but including the pi. Another way you could think about this is the closed interval from 0 to pi with the single number pi over 2 removed from it. Keeping in mind that the principal square root is not negative, I now want to look at integrals that might involve square root of u squared minus a squared. It's worth mentioning that doesn't make sense for all values of u. If u is close to 0, then I'll be taking the square root of a negative number, which isn't allowed in the reals. This only makes sense when u is either larger than or equal to a or smaller than or equal to -a. So this is going to match up with our description of the secant. Let's let u equal a times secant of theta, where theta is contained within the range of numbers that we have previously stated. In order to do our integration problem, I'm going to have to know the value of radical u squared minus a squared. So let's calculate that. Radical u squared minus a squared, radical a squared secant squared theta minus a squared. Underneath the radical sign, I'll factor an a squared out. This is all going along in a way that's very similar to what we've done before. Now, as we've stated previously, we take the a to be positive, so radical a squared will just be a. If you want to be picky about it, then the square root of the square of tangent of theta should really be absolute value tangent of theta. In our previous substitutions, it was always absolute value cosine theta or absolute value secant theta, and because of the range of theta values that we were using, those quantities were always non-negative, so we could just drop the absolute value signs. Unfortunately, this isn't the case now. The thetas that we're using can be split into two categories, one between 0 and pi over 2, the other between pi over 2 and pi. If you think back to the unit circle, that first category of angles is going to correspond to tangent of theta being non-negative. Also, within that range of angles, secant of theta is at least 1. A times secant of theta is at least a. So this corresponds to the u being bigger than or equal to a. In this case, Absolute value tangent theta is just tangent theta since it is positive. In the second category, angles that are at least 90 degrees but no more than 180, the tangent is negative. It is not possible for absolute value tangent theta to equal tangent theta, except in the exceptional case where it's 0. Absolute value of tangent theta, in this case, is the negative of tangent theta. This corresponds to the situation where the secant of theta is less than or equal to -1. A times secant of theta will be less than or equal to -a. This will correspond to the other situation in which the radical makes sense, u being smaller than or equal to -a. So to summarize, if I have an integral that involves an expression like radical u squared minus a squared, I'll make the substitution u equal a secant of theta, where theta is within this complicated set of values that we figured out. In that case, radical u squared minus a squared is either a times tangent of theta, in the case where u is larger than or equal to a, or -a tangent theta if u is less than or equal to -a. This complication is solely due to the fact that we had to use a non-centered interval of theta values in order to get a reasonable inverse cosine function. As an example of this kind of thing, let's look at the integral of x squared over radical x squared minus 4 with respect to x. We're looking for patterns here, most recently u squared minus a squared. If I identify the u as x and a as 2, the quantity underneath the radical sign is of that type. We'll let u equal a secant of theta. That is to say, x is 2 secant of theta. The radical on the bottom of the fraction could be 2 tangent of theta in the case where x is bigger than or equal to 2, or it could be -2 tangent theta if x is less than or equal to -2. Since x is 2 secant of theta, dx is 2 secant theta tangent theta d theta. The radical on the bottom of the fraction is either 2 tangent of theta or -2 tangent theta, depending on whether x is bigger than or equal to 2 or less than or equal to 2. These two integrals are the same except for the sign. So in what follows, we'll work out the first integral. At the end, we'll note that that result is good only if x is bigger than or equal to 2, and then put a negative sign on it to get the rest of it. Using a previous result, the integral of secant cubed is 1/2 multiplied by secant tangent plus natural log absolute secant plus tangent. Combining the 1/2 and the 4, we find that our antiderivative is 2 multiplied by the quantity secant theta tangent theta plus natural log absolute value secant theta plus tangent theta plus a constant. This completes the problem except for converting it back into x values. Using the fact that secant of theta is x over 2, cosine of theta is 2 over x, drawing the familiar right triangle, the third side is easy to figure out. X squared is 4 plus the third side squared. The third side squared is x squared minus 4. The third side must be square root of x squared minus 4. Except for algebraic simplifications, this is our answer In the case where x is bigger than or equal to 2, when x is less than or equal to negative 2, I just have to put a negative sign on this. This is the third of our 3 different types of trig substitutions. I hope all of this has been clear enough and that everyone's having a good day. I'll talk to you again soon.